Namaste everyone. Welcome to class 11, chapter 4, Mathematical Induction. Today in module 2, we shall be covering recalling steps of principle of mathematical induction, proving mathematical statements involving sum of the terms and proving mathematical statements involving product of the terms. In module 1, we learnt introduction of deduction and induction method, understanding mathematical induction by illustrations, and principle of mathematical induction steps. The principle of mathematical induction steps. For a given statement Pn involving natural number n such that the statement is true for n is equal to 1, that is P1 is true. This is the main basic step in mathematical induction. To start proving any mathematical statement, we need to verify it for n is equal to 1. Only then we can proceed further. Then the next step comes, we assume the given statement Pk is true. You need to remember, we assume it. It is not given. We assume that Pk is true. We shall show if the statement Pn is true for n is equal to k, where k is some positive integer, then the statement is also true for n is equal to k plus 1. It means the truth of Pk implies the truth of Pk plus 1. Then we conclude that Pn is true for all natural numbers n. Now, with the help of an example, we will understand the process of mathematical induction to prove any mathematical equation or statement. Here it is a question number 2 of your exercise 4.1 NCERT. Prove the following with the help of principle of mathematical induction for all n belonging to natural numbers. Here we are given the statement that sum of cubes of natural numbers is equal to n into n plus 1 by 2 whole square. We need to prove this by using mathematical induction. How we proceed further? First, as I told you that we will be doing it, verifying it for P1. Replacing n, here replacing n by 1. Left hand side, as in the left hand side, 1 means only one term. One term means first term. So, left hand side is 1 and right hand side we will just replace the n by 1 and we will get this as also 1. Therefore, left hand side is equal to right hand side and P1 is true. Now, we can proceed further. Let us assume Pk is true where k is any positive integer. Pk, we are writing the same statement again, the given statement, only by replacing n by k. As you can see, we have replaced n by k and we name this equation as first equation because we will be using this equation for further proving the statement. Now, we shall prove that Pn is true for n is equal to k plus 1. Now, what we need to do is, we will be replacing k by k plus 1. Wherever there is k, we will replace it by k plus 1. Because in this statement, we were taking the sum of k terms. Now, we are taking the sum of k plus 1 terms, sum of cubes of k plus 1 term. Now, here also after replacing k by k plus 1 is k plus 1 plus 1, that is k plus 2 whole square. Now, in the next, we will consider only left hand side. Left hand side, you recall, if it is k plus 1th term, then what is the kth term? Just previous term. Previous term was k cube. Previous to the last term, this is k cube. This will be replacing, we will be replacing this much part from equation 1. Because in Pk, 1 cube plus 2 cube plus 3 cube plus 4 cube till k cube is equal to this term. We will substitute this term in place of this part. This is here and then the last term of left hand side. Adding this, we will solve it taking it 2 as LCM. Here you can see we have taken here k plus 2 whole square is there in both the terms. In this term as well as this term, we have taken k plus 1 whole square common. Here we are left with k square by 4, because here 2 square will become 4, and here we are left with k plus 1 in this term. Now we shall prove that Pn is true for n is equal to k plus 1. That is, Pk plus 1 is 1 cube plus 2 cube plus 3 cube plus 4 cube dash 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 plus k plus 1 cube. Means till k plus 1 1th term, we are finding the sum which is equal to k plus 1 into k plus 2 divided by 2 whole square. Now, as you know, we have done in earlier slide, this expression was after taking k plus 1 whole square common, we were left with this. We can take 4 as LCM and multiply it with this, and this comes out to be k square plus 4k plus 4, which is nothing but a quadratic equation. We can factorize it, or this is also a square plus 2ab plus b square. We can compare it with this identity and we can find out that it is k plus 2 whole square. This is nothing but k plus 2 whole square. Now this expression is this. We can take this whole square as a common square. Inside we can see k plus 1, k plus 2, 4. Inside the bracket will become 2, and this is whole square, which is nothing but our right hand side, which was to be proved. Therefore, we can say that our statement Pn is true for whenever there is n is equal to k plus 1. Pk plus 1 is true. Now we can conclude that Pn is true whenever n is any natural number. This was all about this. Now another question from your exercise 4.1, that is question number 10. Prove the following with the help of principle of mathematical induction for all n belonging to n. The statement is 1 upon 2.5. Don't mistake it as it is decimal. This is nothing but a product. 2 product 5 or 2 multiplied by 5 plus 1 upon 5 multiplied by 8 plus 1 upon 8 multiplied by 11 till nth term. This term comes out to be this, and this is equal to n upon 6n plus 4. Now, as the principle of mathematical induction step says, we will prove it for P1. For P1, left hand side means first term is nothing but 1 upon 2.5, which is 1 upon 10, and on right hand side we need to replace n by 1. After replacing it by 1, what do we get? We get 1 by 10, which is again left hand side is equal to right hand side. We can say that P1 is true. Now we assume that Pk is true. As the next step says, after P1, we assume Pk is true. What we are required to do here? We will just replace n by k in each step, and this becomes the statement for Pk, which we name it as equation 1. We will be using it further for proving the statement. We shall now prove whenever Pk is true, Pk plus 1 is also true. For that, what we are doing? We are replacing k by k plus 1. Wherever there is a k, we will replace this k by k plus 1. As you can see, k by k plus 1. Then this place, k plus 1. Numerator, this is also k plus 1. This was missed. And here also k plus 1. Now consider left hand side of this statement. In this left hand side, this is the last term. Last term means k plus 1th term. What is the previous term? Previous term was this one, kth term. If we write the previous term, it becomes this is the kth term and this is the k plus 1th term. As we discussed earlier, we shall now prove whenever pk is true, pk plus 1 is also true. Now what is pk plus 1? The statement we have rewritten it again, which is 1 upon 2 into 5 plus 1 upon 5 into 8 plus 1 upon 8 into 11. That can be in general form written like this: 3 k plus 1 minus 1, and in place of this second term 3 k plus 1 plus 2, and which will give us this result. This we need to prove. Now in the previous slide we left the solution or expression till this expression, where this expression is nothing but equation 1. We mentioned it that we will be using it later, and from equation 1 we will be putting its value. Now this is the kth term, k plus 1th term, and this is kth term, k plus 1th term, because wherever there was k we have put k plus 1. As I told you, we will replace this entire expression by k upon 6k plus 4, and again this is k plus 1th term as it is. We will be adding. We can split 6k plus 4 into, by taking 2 outside, 3k plus 2, and solving this 3k plus 3 minus 1, which will give us 3k plus 2. When we will open this, 3k 3 plus 2, which will give us 3k plus 5. Now as you can see in this first expression, 1 upon 3k plus 2 is common. This is also there, and 1 upon 3k plus 2 is also there in the second expression. So we can take this term common, 1 upon 3k plus 2. What we are left with inside the bracket, here k is left and 2 is left in the first expression. After taking 1 upon 3k plus 2 common outside, we are left with 1 upon 3k plus 5 inside. Here, after taking this LCM of these two terms, 2 and 3k plus 5, the LCM is 6k plus 10, and cross multiplying it with these terms, k multiplied by 3k plus 5 and 2 multiplied by 1, we will get this expression, which is a quadratic equation. Now as you can see in this numerator, we have this quadratic equation, where this is 5k is the middle term, which can be broken into 3k plus 2k. From these two terms we can take 3k outside, and from these two terms we can take 2 common. As you can see here, after taking 3k common, we are left with k plus 1 in the first two expression, and after taking 2 common from last two expression, k plus 1 is left inside the bracket, and from these two expressions we can take k plus 1 common. After taking k plus 1 common, 3k is left here and 2 is left here. As you can see in the numerator and denominator, 3k plus 2 is there, the same term is there. We can cancel out these two terms, and what do we get? We get k plus 1 upon 6k plus 10, which can be further broken. This 10 can be further broken into 6 plus 4 like this. Now we can take 6 common from these two terms. As you can see, after taking 6 common, we are left with k plus 1 in the denominator plus 4, and in the numerator we already have k plus 1, which is nothing but right hand side, which is to be proved. Therefore, we can say pk plus 1 is true whenever pk is true. And we conclude that Pn is true for all n where n is natural number. This way we can prove any mathematical statement by using mathematical induction. Now we move to next question. This is the question number 4 of your exercise 4.1. The question is, prove the following with the help of principle of mathematical induction for all n belonging to n. The statement is 1.2.3. As I have already told you, this dot does not mean decimal. This dot here represent the product or multiplication. So we will read it like 1 into 2 into 3 plus 2 into 3 into 4 plus 3 into 4 into 5 plus, this is the general term or the last term of this equation, n into n plus 1 into n plus 2, and we need to prove it that it is equal to n into n plus 1 into n plus 2 into n plus 3 divided by 4. Now, as this is the basic step of any mathematical induction process, that we consider the statement as Pn. The first statement we name it as Pn, and then the next step comes to verify the statement for n is equal to 1, that is the basic step. All the steps for all the questions, these 3 steps are common. First, to prove it for n is equal to 1, then assuming it for n is equal to k, and then proving it for n is equal to k plus 1. So, here we are proving it first, verifying it for P1, taking left hand side means this is the left hand side, and on left hand side while we are talking about n is equal to 1 means we are talking about first term. Here this is the first term. So, left hand side first term result is 6, and when we talk about right hand side we need to substitute n by 1. Wherever there is n, we will replace it by 1, and this is the case. This is 2, this is 3, and this is 4. 2 multiplied by 3, 6, 6 multiplied by 4, 24 divided by 4 gives us 6. So, we can say that left hand side is equal to right hand side, therefore, P1 is true. So, this gives us signal that we can move further by assuming that pk is true, where k is any positive integer. After assuming that pk is true, we shall prove that the statement is true for pk plus 1. Before moving to pk plus 1, let us write pk. What is pk? What is the difference between the statement pk and pn? Only the difference is wherever there is n, we will replace it by k. So, this gives us 1 into 2 into 3 plus 2 into 3 into 4 plus 3 into 4 into 5 plus, that is plus the kth term, which is k into k plus 1 into k plus 2 is equal to k into k plus 1 into k plus 2 into k plus 3 divided by 4. And as we have assumed that this statement is true, we will consider this statement as equation 1. We will be using this result for further proving pk plus 1. Now, we need to prove that Pn is true only when for n is equal to k plus 1. So, let us prove it. Before proving, we will form the equation by replacing k by k plus 1. This is our mathematical statement in the form of k plus 1. Here what we have done? We have just replaced k by k plus 1 wherever there is k. Here k plus 1 is there. When we will replace k by k plus 1, k plus 1 plus 1. Here k replacing it by k plus 1 plus 2, and same way k replaced by k plus 1. K plus 1 will be replaced by k plus 2, k plus 2 will be replaced by k plus 3, and k plus 3 will be replaced by k plus 4 divided by 4. We need to prove this result. Now, we will consider left hand side as usual. In every question of this type, we need to take first left hand side. So, in the left hand side, this is the term, this expression which is till k plus 1th term. And what is the term before k plus 1th term? That is the kth term. And the kth term from equation k, as you can see, this is the kth term, k into k plus 1 plus k plus 2, and the next term is k plus 1th term. We can always write previous term and we can also write previous to this, but here we require this term only. Now, I have rewritten the statement to be proved, which is pk plus 1. Now, we got this result from the previous slide that this is till kth term, adding k plus 1th term, and this whole expression, this entire expression will be replaced by the expression from equation 1. What we got in right hand side of equation 1, this whole entire expression will be replaced by that. This was the right hand side of equation 1, and this is nothing but the same expression we have written, which is k plus 1th term of this. Now, after taking this 4 as LCM, this will go there and we can write this expression as k into k plus 1 into k plus 2 into k plus 3 into 4 into k plus 1 into k plus 2 into k plus 3 whole divided by 4. Now, what you can see here in these two expressions? Can you see anything common here? Yes, here term k plus 1, k plus 2, k plus 3 are common, which can be taken outside. After taking these three terms common, what is left here? Here left k and here it is left 4, which will give us k plus 4, and this is the required expression, which is the right hand side, which is to be proved. This was the expression we needed. So, left hand side is equal to right hand side, and thus we can say that the statement pk plus 1 is true whenever pk is true. Whenever we write this statement, you must have noticed we write whenever pk is true. We are proving pk plus the truth of pk plus 1 when we assume that pk is true. If pk is not true, we cannot prove that pk plus 1 is true. So, after when we have proved it for pk true, pk plus 1 true, now we can say that the statement Pn is true for all n, where n is a natural number. Now, we shall move to next question. This is a question number 9 of your exercise 4.1. The question is, prove the following with the help of mathematical induction for all n belonging to natural numbers. What is the statement here? The statement is 1 upon 2 plus 1 upon 4 plus 1 upon 4, 8 plus 1 upon 2 to the power n. How we reach to 2 to the power n? This is the general term, because you must be noticing this is 2 to the power 1, this is 2 to the power 2, in the third term 2 to the power 3, whichever is the term, that is the power of that. So, this is the nth term, so therefore it is 1 upon 2 to the power n, which is equal to 1 minus 1 upon 2 to the power n. We need to prove this. As you know, the first and the basic step is to assume the given statement as Pn, and we will consider this statement as Pn. The given statement will be first named as Pn, rest the statement is same. What is the next step? The next step is we need to verify it for n is equal to 1. For n is equal to 1, let us see on the left hand side for proving P1, we need to take left and right side both. Left hand side means first term. This 1 means one term. So, one term means first term. The result of first term is 1 by 2, and while taking right hand side, we need to replace this n by 1. When we put it 1 here, 1 minus 1 upon 2 to power 1, this will give us 1 minus, let me write again, this is 1 minus 1 upon 2 to power 1. So, 1 upon 2 subtracted from 1 will give us nothing but 1 by 2 only. left hand side is also 1 by 2, right hand side is also 1 by 2. So, left hand side is equal to right hand side. Therefore, our statement P1 is true. We can say that our statement P1 is true. Now, when the truth of P1 is established, the next step is to prove or to assume that Pk is true. We will be assuming that Pk is true where k is any positive integer. You need to remember these steps. Whenever we are writing Pk is true, we need to mention that k should be positive integer. It is not for negative integers. So, Pk statement can be written easily. By now, you must have understand why just by replacing n by k, wherever there is n, we will replace it by k and we get this expression for Pk. The same way here, 1 minus 1 upon 2 to the power k, and the basic step, we take it as equation number 1. We will be using it further. Now, we shall prove that Pk plus 1 is true. Once we assume that Pk is true, the next step is to prove Pk plus 1 is also true. Here, k is replaced by k plus 1. The same statement goes. This is the expression involving only k terms. What we have done is, we have added the successive term, which is k plus 1th term. So, this becomes the expression for k plus 1th term, and here also we will replace k by k plus 1. Wherever there is k, we will replace it by k plus 1. So, this becomes 1 minus 1 upon 2 to the power k plus 1. Now, writing this expression again, which is to be proved, we need to prove this expression. We have written this again, and considering only left hand side, we will be taking this much part, this much part which comes in the left hand side, and as you know, till term kth term, this entire expression is till this place. This is nothing but 1 minus 1 upon 2k. How? This we have taken using equation 1. We have already told that we will be using it further. So, till k we are writing this expression. Now, solving it further, we are breaking this 2 to power k plus 1 like this by law of exponents. As you know that power of, if we can write a to power m plus n, we can break it like a to power m dot a to power n. Dot means multiply. We can break this power into two parts by writing it in product. The same way we did it here. 2 power k plus 1 is broken into 2 power k into 2 power 1. Keeping this expression as it is and just solving it further. Now, what you see in these two terms, 1 upon 2 to power k is common. Therefore, from these two terms, keeping 1 as it is, from these two terms we have taken 1 upon 2 power k with negative sign outside. What is left inside the bracket? Here, when we have taken this whole expression outside, only 1 is left, and when we have taken this expression outside, 1 upon 2 is left inside, and which is very simple. 1 minus 1 by 2 is nothing but 1 by 2, and here we are left with 1 upon 2 power k into 1 upon 2, which can be written further as 1 upon 2 power k plus 1, and this is the required expression that we wanted to prove. Therefore, this is equal to right hand side, and we can say that Pk plus 1 is true. Whenever Pk is true, you need to write this statement whenever you write this. And the further we can say P1 is true, Pk is true, Pk plus 1 true, we can conclude that Pn, the mathematical statement Pn is true for all n belonging to natural numbers. So, here in this module 2, today we learned the steps of mathematical induction. We proved some mathematical statements involving sum of the terms and proved mathematical statement involving product of the terms. That's all for today. In next module 3, we shall cover more examples on principle of mathematical induction involving inequalities and divisibility of terms problem. Thank you.